I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
Yeah, my name's Clive Neal. I'm a professor of lunar geology at the University of Notre Dame in Indiana. And I'm going to talk to you today about the crust of the moon and lead you on a journey of what we've understood from Apollo and since Apollo and why we should go back. Going back to the moon is going to be important for a number of reasons, not least of which is science, but also more importantly for exploration and maybe the economy. Creating jobs outside of NASA, that is off-planet, becomes a reality if we then use the moon as an enabling asset to then go to Mars. So understanding the moon becomes very important, not only about how the moon formed, but what is available on the moon that we can use to make the moon that enabling asset. So if we look at the moon, we already know that it's the closest planetary body to Earth. And you can also see in relative to the other planets that the moon is the smallest planetary body. So being small, it means its heat engine shut down a long time ago. We know from Apollo that the surface of the moon is very old, maybe 3 to 4 billion years old. There is no atmosphere on the moon anymore, but what we have is meteoroid impacts. So if we look at the moon then, the moon represents an end member because the earliest stages of differentiation, how that planet evolved soon after formation, is now frozen in time. And it gives us then an end member to look at how Earth, Venus, Mars, and Mercury could have also evolved. So if you look at the moon, you can see here we've got the near side and the far side from the Lunar Reconnaissance Orbiter camera, the wide-angle camera. These are mosaics that have been put together, and there are very notable differences between the near side and the far side. You can see on the near side we have lots of areas which are darker. These are seas or mare that were formed by basalt erupting onto the surface 3 billion years ago, although we now know maybe just a few 100 million years ago. If we look at the far side, it is very different. We can see that it is dominated by the Highlands crust material, much lighter material, because the Highlands crust is made up of this mineral called plagioclase, a calcium aluminium silicate. And we see this distributed across the moon. Very few areas of mare on the far side because the crust there, we now know, is much thicker than it is on the near side. So if we then take a very broad brush look at our moon, we can see that we have our mare or maria on the near side, where we've had eruption of lavas onto the surface and resurfacing of much of the near side of the moon through these eruptions. We then have these highlands crustal areas which are dominated by the mineral plagioclase. So if you go out at night and you can see the moon, the lighter areas represent those highlands crustal areas. This is a very old surface of material, some parts of which were actually formed during the initial formation and differentiation of that particular planet. Another important feature are these impact craters. You can see here we've got one into the Maria and one into the highlands areas, but this means that our moon has been under attack pretty much since it formed by impacts that don't burn up because there's no atmosphere on the moon. So they go in and they can redistribute material around the moon and redistribute that crustal material that we sent Apollo astronauts to pick up and bring back. So if we look at the samples that we have from the moon, you can see that the landing sites for Apollo and the Soviet lunar robotic return missions are highlighted here. You can see that the Apollo samples are collected all from the near side and the central near side, with the lunar 16, 20 and 24 missions going to the eastern limb of the lunar near side. Now, these Soviet lunar missions only brought back less than 1 kilogram of material, whereas the Apollo missions brought back a total of 382 kilograms of material. Now, in the late 1980s, we recognized that meteorites in the collection were actually derived from the moon. We compared compositions that we had from Apollo samples with those from the meteorites, and we can actually see that these were derived from the moon. But as I said earlier, exactly where on the moon, we just don't know. But they are giving us a new look at the moon and starting to cast some doubt on some of the conclusions drawn by just looking at the Apollo samples. Since Apollo, we've had a lot of orbital missions that have gone around the moon and given us global data sets of the entire moon. With those data sets, we can now define different terrains. You see in the diagram we have PKT and FHT. PKT means the Prosolarum creep terrain. The FHT is the feldspathic highlands terrain. So if we deal with the PKT, this is a very special area because it is enriched in this component we term creep. Now, creep, K-R-E-E-P, represents potassium, rare earth elements, and phosphorus in terms of our signature that we have there. Now, what it means is that we have a lot of materials that are enriched in these elements in the PKT. If you go outside there into the feldspathic highlands terrain, they are very much lower abundance, if not devoid of that particular signature. So it showed us that we had distinct terrains, that the moon was not as homogeneous as once thought. And then when we look at these global data sets in relation to the Apollo samples that were brought back, we can see that the Mare basalts in the Apollo collection showed a bimodal distribution on the basis of titanium. Now, if we then look at the compositions of basalts from the remote sensing data, we see that no, it's not a bimodal distribution. By far, the most abundant type of basalt is the low titanium Mare basalts. And in some cases, these data sets are defining lithologies that we just don't have any examples of. And we'll come back to that in a little bit. Before we start looking at the crust, lunar crust itself, we have to look at the origin and early evolution of the moon in order to understand where the crust came from, what we actually go out and can see from this planet when we look up at the moon. We need to understand how it formed. Now, we've been informed by samples that came back from Apollo, and it was right after the Apollo 11 samples were returned that the idea of a magma ocean was born. Now, the formation of a magma ocean requires a lot of energy. In looking at how the moon orbits the Earth, the only way that it can really achieve those particular orbits and those orbital dynamics is to be formed by a very violent origin in terms of a collision between two planetesimals early on in the origin of the solar system. You see here depicted that cataclysmic impact between these two planetary bodies. You have the proto-Earth, and then we have the Mars-sized planetesimal that came in and hit it. And most of the material from the crust and the mantle of both planets was ejected out and coalesced to form the moon that now orbits us and we could go out and see. But the energy involved in both the impact between the two planetesimals and then the accretion of the material to form the moon meant that it was very hot and formed this magma ocean. Now, this magma ocean means we had a lot of energy being involved and a lot of evaporation, and it may even be that the moon had a very thick but metal-rich atmosphere during this magma ocean time. As the moon started to cool down, we started to get this quenched crust. And I don't know if you've ever seen videos of lava pools in Hawaii, but there's a lot of convection going on, and these quenched crusts get taken back down into the magma and assimilated back into it. So this was a very temporary crust until the quenched crust could thicken and then maintain its integrity rather than being torn apart by the convection of the magma ocean. Now, as the magma ocean continued to cool, we started to see minerals come out of it. Those with the higher melting point would crystallize first. Those that had a density greater than that of the magma would sink and form the mantle of the moon. As the evolution of that magma ocean continued, we started to see different minerals precipitating out as the magma composition changed. Eventually we had this wonderful mineral plagioclase crystallized, and plagioclase would have been less dense than the magma, so it would have floated. And you could see in the blue area on the diagrams where that plagioclase would float to the top. It would sit underneath that quenched crust lid, the primordial crust itself, and we now call that plagioclase crust, well, maybe the primordial crust, because we actually can have samples of it, and we'll get to that in just a little bit. The other thing I want to point out here is this creep name again that comes out. This is the last dregs of the magma ocean. As the magma ocean crystallizes, the elements that don't go into the crystals become concentrated into the residual magma. So the potassium, the rare earth elements, phosphorus, thorium, uranium, all become concentrated in this creep component, and it becomes one of these signatures that we know, if we're going to model this magma ocean, that we have to then replicate. So we'll focus on the rare earths because these are an important series of elements in the periodic table. These are the lanthanide series, and we can see that they're divided into the light and the heavy rare earths. I'm going to be referring to the light and heavy rare earths as we continue on. So if we look at our mineral plagioclase, now plagioclase likes europium. When plagioclase forms, it will actually incorporate the europium in the 2+ form much more than the other rare earth elements. So what we end up with in the top profile here is we can see that plagioclase will have a positive europium anomaly. That means then that the magma from which that plagioclase came from now has a negative europium anomaly. And we see this negative anomaly in all the Mare basalts that are erupted, suggesting that their source has seen this plagioclase with removal. The other important thing about the rare earth elements are samarium and neodymium. You can see those highlighted here, and one of the isotopes of samarium decays to the 143 isotope of neodymium at a constant rate. This radioactive decay is very important when we come to age dating these very ancient samples that have been brought back from the moon. So in our lunar magma ocean model then, and this is just a model, and there have been several attempts to actually show what proportions of minerals came out and at what time. Now this is going to be dependent upon our magma ocean starting composition, and you can see here there are 5 models that are shown in the diagram, and what I want to point out is the point at which our plagioclase rich crust could start to form. Now basically what this tells us is that the magma ocean has to be 2/3 crystallized before we can start to have plagioclase forming. This means we would have a very thick quenched crust lid sitting on top of that magma ocean, but we would also have this pressure on the crystals as they were being formed. So we would have then a long time between initiation of magma ocean and formation of the crust that we can now see from Earth. So you can see here the diagram shows that we have an initial quenched crust until we get plagioclase, and then plagioclase would float and sit beneath that quenched crust until it is exposed through the meteoroid impacts that we can still see evidence of, and still see it happening today through impact flashes. So our crust then, the initial crust would have been this quenched crust. The lunar magma ocean crust forms after a while when we start to see plagioclase crystallizing out of that magma ocean. Now another mineral that is also important in our modeling is garnet. Now garnet, like plagioclase, is an aluminium-rich mineral, but it needs to form at pressure, and on the moon it has to be below about 500 kilometers. Now garnet retained in the source gives important information or imparts important information on the magmas that are then produced. Because what we see with garnet, you can see the mineral incorporates the heavy rare earths over the light rare earths. So if you extract garnet from a melt, you will enrich the melt in the lights and deplete it in the heavies. Conversely, if you have garnet in the source region and you melt it and retain garnet in the source region, that melt will be enriched in the light rare earths and depleted in the heavies. So we can use that then to take the 5 magma ocean models to look at what happens to our rare earth element sequence. And as we go through here, you could see that they're modeling the different percentages that come out. And in this model from Snyder et al. 1992, the creep signature, which are the red squares in each one of these diagrams, is best modeled if 3% garnet is also extracted from the magma ocean along with plagioclase. If we then look at the Elkins-Tanton model of 2011, we can see the same sort of thing, that garnet gives you a much better representation of the creep that we know exists on the moon. If we then look at the Lin et al. Model, this is a bit different. They used anhydrous conditions, and what we see here is that some garnet is required, but eventually it needs to, as the mantle fills up with these crystals, we get a reduction in the amount of garnet to nothing. But if we then combine the small amount of garnet and in the early stages of plagioclase crystallization, we then see it disappear towards the end. We can pretty much recreate that creep signature. Similar sort of thing with the Charlier et al. Model in 2018. And interestingly, the Rapp and Draper model of 2018 does not require any garnet to generate that creep. So you can see these are all models. They are giving similar signatures, but how we get there is very different. So there are a lot of questions in how the magma ocean differentiated and also how the lunar crust formed. So what have we learned from Apollo? So what we have here is a diagram that shows the amount of anorthite, or basically calcium, in our plagioclase. And you can see the anorthite is represented to the amount of calcium divided by the amount of calcium, sodium, and potassium. And it's plotted against the magnesium number. And our magnesium number is the amount of magnesium over the amount of magnesium plus iron in the given mineral. And we're dealing with mafic minerals, which mean olivine and pyroxene. And what you can see here in the Highlands crust, we actually have our Pharoan anorthosite, or our fans, forming a vertical trend on this diagram. We then have what are termed the Highland magnesium suite, forming above that and leading down to the bottom left of that diagram, leading into the Highlands alkali suite. If we look then at the Pharoan anorthosites, we can see that they are mineralogically diverse. The different colors there represent different mineral percentages within our Pharoan anorthosites. So we have a very diverse suite of materials that we think was the initial crust from the magma ocean there. And to give you an idea of what they look like, you can see 2 hand specimens from the Apollo collection. Now, this vertical trend becomes quite problematic, because you can see here in the diagram of anorthite against magnesium number what the expected trend is if you are just crystallizing plagioclase from a magma. We expect it to go to the bottom left. What our Pharoan anorthosites are telling us is that no, this is a vertical distribution, and that the anorthite content of our plagioclase does not change very much. Now, experimentation has shown us that if we have relatively high pressure, and this would require a quenched crust of about 70 kilometers thick, we would end up buffering that anorthite composition in our plagioclase and getting that trend as we see on the diagram. So we do require an early thick quenched crust in order to allow this distribution to actually be formed. So from Apollo then, we have our Highland samples that divided into 3 basic suites. We have our Pharoan anorthosite suite, where you can see this is used as FAS or FAN, FAS or fans, and these are believed to be the primary samples of the primary crust formed by plagioclase flotation within the lunar magma ocean. The Highlands magnesium suite, it represents secondary intrusion, so we had melting of the interior after the formation of the Pharoan anorthosite crust, and these magmas went up and intruded that fan crust. Then we have the Highlands alkali suite, and these are potentially an evolved M member of the Highlands magnesium suite, and these also intruded the Pharoan anorthositic crust. So if we look at the Pharoan anorthosite suite, Apollo 15 was tasked with going and finding some of these ancient samples. They were given the information that these would have been plagioclase rich, and they would be very old because they would represent the actual crust of the moon. So let's just hear a little bit about what the Apollo astronauts from Apollo 15 actually said as they were finding what we term 15415, the Genesis rock.
Oh man, look at that. Look at the glint. Almost see twinning in there. Guess what we just found? Guess what we just found? I think we found what we came for. Crystalline rock, huh? Yes, sir. You better believe it. Yep, sir. Plage in there. Almost all plage. She likes it. As a matter of fact, oh boy, I think we might have ourselves something close to anorthosite. Because it's crystalline in there. It's just a bunch of, just almost all plage. What a beaut. That is really a beauty. And there's another one down there. Yeah, we'll get some of these.
Now the Genesis rock becomes very important because you can see that it is firmly within the Pharoan anorthosite field. It is very coarse-grained, consistent with our cumulate from a magma ocean, crystallized slowly, gives you big crystals. And you can see there the hand specimen also of this particular sample. Now, how old is the lunar crust, and how do we age date these anorthositic samples from the lunar crust? Coming back to our rare earth elements again, you can see here we have lanthanum through lutetium, but we're interested in our samarium and neodymium. And remember, 147, the isotope 147 samarium will decay to the isotope 143 neodymium at a constant rate over time. So what we see here then is how we talk about the samarium neodymium chronometer in terms of the rare earth patterns. And we can see here a chondritic pattern, which is a chondritic meteorite pattern, which is flat on this particular representation. And you can see where samarium and neodymium are actually present. If we have a light rare earth enriched rare earth profile, we can see that we have actually decreased the samarium to neodymium ratio. If we have a light rare earth depleted rare earth element pattern, we have now increased the samarium neodymium ratio. So in terms of evolution of these particular isotopic systematics, we're looking at the ratio of 143 neodymium to 144 neodymium. They're both neodymium, they're just different isotopes. 143 neodymium changes because it is radiogenic. It is formed by the decay of 147 samarium. 144 neodymium is stable. And you can see that the evolution line, as time progresses, you can see what happens if we enrich the rare earth element profile in light rare earths. We actually then slow down the increase in the 143, 144 neodymium ratio. If we deplete that rare earth element profile, we would then increase the change in that 143, 144 neodymium ratio. So understanding what the samarium neodymium ratio is of our anorthosites, as well as what the 143, 144 neodymium ratio is, we can then start to get an idea of age, how long that rock has been around since it crystallized. Now, if we then look at the ages that have been determined for our Pharoan anorthosites, we can see here that we've got a range of ages, and our model suggests that these ages should be older than our Highlands magnesium suite and our Highlands alkali suite. And We can use multiple chronometers to do this, but samarium neodymium is a pretty robust chronometer, so we're going to focus on that one for the purposes of this talk. However, we do have issues. If we look at the age range here, it's more than about 200 million years. That it's much too long for a lunar magma ocean to be kept liquid. And also, if you look at 60025, it's on there twice. 60025 has given two distinct samarium neodymium ages for the same sample. That is a problem, because if it's one sample, it should give the same age no matter how many times you analyze it. Well, one way around the length of time for the defined by the Faroan and orthosites is to give it an insulating lid. And this is a model that was proposed by Elkins Tanton et al. 2011 and was then focused more upon by Meyer et al. And what we can see here, that if you have the moon forming, and the orbital dynamics suggest that it was much closer to the Earth than it is now, and we're actually losing the moon at the rate of several centimeters a year as it degrades its orbit. And what we can see then is that if we have an insulating lid or a quench crust coupled with gravitational attraction and friction and heating, we can actually keep the magma ocean alive for longer than 200 million years. But remember, this is just a model. If we look at the Highlands Magnesium Suite, we can see here that we've got a lot of samples that have been dated by the samarium neodymium technique. They also form a range of ages, and you can see there that the uncertainties are also much different in some samples versus others. You can see that also that the Highlands Magnesium Suite, as typified by 76535, this has this equilibrated texture to it. It's a beautiful rock, but the texture suggests that something else has happened to this particular sample since it formed. Now, if we then combine our Faroan and orthosite suite and Highland Magnesium Suite samples with samarium neodymium ages, we have causes for concern. Number one, we have large uncertainties in several of these samples. Number two is that we have different ages for the same sample in a number of cases, both for the Faroan and orthosites and also the Highland Magnesium Suite. And maybe most importantly is that we have overlapping Faroan and orthosite and Highland Magnesium Suite ages. So the model that the Faroan and orthosite crust formed and the Highlands Magnesium Suite then intruded into it is now in question. If we then combine the Highlands Alkali Suite, you can see the zircon ages there also overlap with both the Faroan and orthosites and the Highland Magnesium Suite. And if the Highlands Alkali Suite is an evolved M member of the Highlands Magnesium Suite, they should be younger than those. So we should see an age progression, and we don't. So we have to go back and look at the rocks themselves. Getting an age date and doing chemistry on these samples is one thing, but how are the minerals related to each other, and what is the texture like? So what we have here are a number of Faroan and orthosuite samples that have been age dated by the samarium neodymium technique. And what you see immediately, they have a very broken up texture, or what we term brecciated texture. This means that the impacts, meteoroid impacts that have been ongoing since these samples were formed have severely affected the texture of these rocks. Not only have they been mechanically brecciated, they could have been mechanically mixed with other lithologies, because we know from lunar reconnaissance orbiter images that impacts are still ongoing today. So this impact, it has to be taken into account, and how it's mixing these rocks. And yes, we may have a Faroan and orthosite sample, but it may be made up of different Faroan and orthosites of different ages, and that may be explaining some of the large uncertainties that we see in the samples, and maybe even the distinct ages that we see for some of these samples as well. For example, 60025. The Highlands magnesium suite samples are not faring any better either. 72215 is showing something that is undergoing equilibration. We're starting to see that interlocking texture that we see depicted very well by 76535, suggesting that they have been equilibrated and heated in the solid state, allowing this equilibrated texture to develop. Then we have 15445, where we see a very shocked material where we can't see any defined crystal boundaries as such. They have been blurred due to the effect of this incredible shock through the meteoroid impact. Another issue comes from the data that's been gathered from orbit since Apollo. These are data from the Moon Mineralogy Mapper. This was flown on the Indian Chandrayaan-1 mission earlier this century. And what Carly Peters and co-authors have found from these data is that we have lithologies present in the lunar crust that we simply don't have any representation in our current sample suite. These are olivine, orthoperoxine or OPX, and spinel-rich lithologies, affectionately termed ooze by Carly Peters. Now, magnesium spinel is important because it represents another aluminous mineral. We've talked about plagioclase and we've talked about garnet. And now we're finding that we have magnesium spinel in the crust. So various models have been produced. This could be a direct product of the lunar magma ocean. However, it could also be an impact melt cumulate. You have a large impact, you get a lot of melt. It can also differentiate. Or it could be a reaction between magma and a plagioclase-rich wall rock that could also precipitate this mineral spinel. Now, the significance of these data is the fact that the pixel size from orbit is about 250 by 250 meters. And we're getting definitive signatures of spinel, orthoperoxine, and olivine over these areas. What we don't know is the geologic context of these. Have they been intruded into the crust? Are they a layered intrusion? We don't know. We need to do good old-fashioned geologic field work on the lunar surface at some of these sites to truly understand their origin and how they evolved. This would also include sampling. You could have very strategic sampling by an astronaut that would allow us, as we saw with 15415, that would allow us to get a much better insight into these new lithologies that we knew nothing about until the Chandrayaan-1 mission. Japan also had a mission, Kaguya, affectionately termed Selene, and what we see from the data that they produced is that they focused a lot on the crust. And we see that there is a dichotomy between the composition of the crust on the near side with that on the far side. We knew that there was a thickness dichotomy, as we see with the Mormari on the near side and less on the far side. But what we can now see through compositional evidence is that the Selene mission has showed us that the far side crust is more magnesium than the near side. And it may be the magnesian anorthosite rather than the Pharoan anorthosite is the dominant composition on that thicker crust on the far side. Now, this has implications of when plagioclase comes out of our magma ocean. We would have to have a much higher aluminium content in that magma ocean to affect that. But magnesium anorthosite means that it comes out much earlier in the sequence than does the Pharoan anorthosite that we've modeled using the Apollo data. So if we look then at the feldspathic highlands, we can see here are the Apollo data, but we've now got these lunar meteorites which contain an awful lot of highlands materials. They are representative of the crust in the area from which they were derived, but we just don't know which area they were derived from. We can assume far side, but where on the far side, we don't know. So if we then take these two fields, you can see here the Apollo magnesium suite and the Pharoan anorthosites, and we compare those with the data that have come from the feldspathic or highlands lunar meteorites, you can see that these are predominantly Pharoan anorthositic. However, they greatly expand that range of Pharoan anorthosites that we got from the snapshot from the Apollo samples. The problem here is that the Apollo samples have been affected by the Imbrium ejecta. They form a very narrow field that we now know is narrow because we can compare them with these feldspathic meteorites. So the lunar meteorites then are showing us that Apollo gave us a snapshot that was, again, not representative of what the rest of the moon actually is. So the models that have been developed during Apollo now have to be adjusted on the basis of new data. If we then look at what we did learn from Apollo, we can see that the differentiation mirrors that from the big intrusions that we have here on this planet. The ones that we have from the still water are not from a magma ocean. They are a large intrusion of magma. And you can see similarities in the trends there of the rock minerals in the rock types that come from still water with those from the Apollo samples. If we then compare that with the lunar meteorites, we see that the lunar meteorites show a much more a broader field in terms of magnesium number in our mafic mineral for a very narrow range of anorthite content in our plagioclase, expanding it. So we have to adjust our story now because Apollo didn't tell us everything. The new data are now testing the hypotheses that have been developed, such as the lunar magma ocean, by these new samples and the new orbital data. So in summary, the Apollo and lunar missions to the moon greatly increased our understanding of the moon. We knew nothing really about the moon until we had these samples coming back. However, since then, we've now recognized that we have new samples in lunar meteorites. We've also had a lot of missions, there's a lot of international interest in our moon now, and a lot of international missions have gone to the moon, and the orbital data shows us that the models previously developed are somewhat lacking. They're being tested, and they need adjusting, or they need to be rethought altogether. We also know that while the meteorites are from the moon, we don't know where on the moon they're from. They're from unknown locations. We need to actually have coordinated sample return from areas well away from Imbrium and the ejecta from that Imbrium basin. And especially we need to go to the far side and see whether or not we can actually correlate the compositions from these lunar meteorites with those that are collected in situ from the far side of the moon. Now, the geologic context of these new samples is critical for developing these new predictive models. We want predictive models because on Earth we have plate tectonics, and we know what plate tectonic setting to go to get resources. If we're going to use the moon to go further out into the solar system, we need to develop infrastructure, and that means living off the land and defining resources. So understanding these new lithologies, how they fit in to the given framework of lunar petrogenesis, is going to be important, and it's going to require geologic field work. And probably the best way to do that is by sending astronauts there who are adequately trained to undertake such an expedition. Now, the geologic context of these new samples is going to be critical for understanding and making predictive models. On Earth, geologists have done field work for many years and have developed these models based around plate tectonics. So if we can recognize a particular setting on Earth, we know where to go and look for specific resources that will fuel our economy. Same as can be said for the moon. The resources will become important as we expand into the solar system. And geologic fieldwork is going to be critical to that. It's going to be required to develop these predictive models. If we can then find out where these resources are, things such as aluminium, titanium, water ice, so on and so forth, we then can start to develop an economy behind that. Because it's not NASA's job to go out and mine regolith. This can be brought in as a commercial venture. We can start to expand the space economy. We can start to then bring in private industry, which is going to be employing people and going to be starting to hiring new people to do that, and thus creating jobs that are going to be a necessity As we expand to the moon to go on to Mars, the resources on the moon can be used to enable Mars. For example, if we look at building structures on the moon for infrastructure, 3D printing becomes important, and knowing that there's titanium and there's aluminium and there's silicon and there's water ice on the moon becomes important. Being able to harness these resources requires commercial participation. So NASA can then expand onto Mars, but can then buy the services and the materials required in order for example, water is a good radiation protection. We can sheath a spacecraft in water. Launching it from the moon, it's much cheaper than launching it from Earth. We know that the water ice is there now. We can then expand upon that. So by building a spacefaring species, we then enable a new sector of our economy. We expand that space economy. And with the USA being in the forefront of this is something that we can lead the world to do. And I think it's important that we use the moon as a stepping stone to do that, although I hate the term stepping stone. It becomes an enabler to do that. The moon is an enabling asset in order to not only go on to Mars, but to expand our space economy into something that is robust and growing, so that graduates from my university, when I ask them, what do you want to do after Notre Dame? They can say, I'm going to go work on the moon. And that becomes science fact, not science fiction. Now, the geologic context of these new samples is going to be critical for understanding and making predictive models. On Earth, geologists have done field work for many years and have developed these models based around plate tectonics. So if we can recognize a particular setting on Earth, we know where to go and look for specific resources that will fuel our economy. Same as can be said for the moon. The resources will become important as we expand into the solar system. And geologic fieldwork is going to be critical to that. It's going to be required to develop these predictive models. If we can then find out where these resources are, things such as aluminium, titanium, water ice, so on and so forth, we then can start to develop an economy behind that. Because it's not NASA's job to go out and mine regolith. This can be brought in as a commercial venture. We can start to expand the space economy. We can start to then bring in private industry, which is going to be employing people and going to be starting to hiring new people to do that, and thus creating jobs that are going to be a necessity as we become a My name's Clive Neal. I'm a professor of lunar geology at the University of Notre Dame in Indiana. And I'm going to talk to you today about the crust of the moon and lead you on a journey of what we've understood from Apollo and since Apollo and why we should go back. Going back to the moon is going to be important for a number of reasons, not least of which is science, but also more importantly for exploration and maybe the economy. Creating jobs outside of NASA that is off-planet becomes a reality if we then use the moon as an enabling asset to then go to Mars. So understanding the moon becomes very important, not only about how the moon formed, but what is available on the moon that we can use to make the moon that enabling asset. So if we look at the moon,